Thank you very much for the organisers for the opportunity to speak to you all today. I'm going to be talking about a couple of projects that we've been running over the last couple of years in collaboration with the Open Force Field Initiative. Firstly, to try to improve the accuracy of torsion parameterization, and secondly, looking at these non-bonded models in force fields. Ultimately, of course, keeping an eye on the accuracy in final free energy calculations. So I will show a couple of slides on free energy at least. But I hope for this audience, I don't need to explain too much that free energy calculations are crucially reliant on the accuracy of these molecular mechanics force fields to model the conformations of the proteins and small molecules and the interactions between them. So just to make sure we're all on the same page in this talk, I'm going to be mostly talking about force fields of this form on the left-hand side here, where atoms are bonded together by harmonic springs, and rotation about rotatable bonds is modeled by cosine expansions. And for non-bonded interactions, we have these Lennard-Jones type interactions supplemented by electrostatic interactions between point charges. So to summarize my talk in one slide, I'm going to start by looking at these torsion parameters, and in particular, looking at how we can develop molecule-specific parameters to supplement the open force field. And secondly, I'm going to be showing a bit more dramatically that we can chuck out the Lennard-Jones interactions altogether and replace them with hopefully something a bit more flexible and accurate. So why do we need to keep on doing this? We've seen in previous talks that force fields are doing pretty well. But of course, if we look at all the problems that are inherently in there, we know that bond stretching and bending is not harmonic. That's not such a big deal for free energy calculations. But certainly these rotations about flexible bonds have to really account for a huge number of stereoelectronic and steric effects, which is difficult to model all with this transferable parameter library. The Lennard-Jones interactions are having to do a lot of heavy lifting in this force field. They've got to absorb lots of quantum mechanical dispersion effects, not just the C6, but the C8 and the C10, and all these inherently quantum mechanical effects that start to happen as you overlap two electron clouds. I won't be talking about it so much here, but just for completeness, electrostatics are not modeled well by a single point charge at the atom center. These need to effectively account for polarization and any anisotropy in the electron distribution. And something that's less often mentioned is that these parameters themselves are usually assigned by atom typing, as we've heard. And historically, maybe not so much nowadays, the provenance of these parameters is often unclear or even forgotten. So that's where the Open Force Field Initiative comes in. So this is an international academic industry collaboration working together to advance the science and infrastructure to build these force fields. So it's led by the people on the right-hand side here, most of whom are in the audience, I think, and by Jeff and Lily on the technical and science sides. So at the heart of this infrastructure is the open source Python toolkit, which enables users to assign parameters to molecules and use them in simulation packages. They've curated a huge amount of quantum mechanical and physical property data that allow you to go away and build your own force fields, but also importantly, all of the infrastructure you need to go and test your force field and unambiguously say, this was a good design decision, that was a bad design decision. And importantly here, everything is done out in the open. So as an external collaborator to the Open Force Field Initiative, I hope I can show you today that I can indeed come in, collaborate, and use all of this infrastructure to hopefully contribute something useful. So I need to dig in a bit more into the infrastructure. So if we start on the left-hand side here, we might have some initial force field. So we can use the toolkit to assign parameters to a bunch of molecules. We can use the Open Force Field Evaluator package to model properties of those molecules. and also gradients of those properties with respect to the parameters. We can use Leaping Wang's very nice force balance software for optimizing the force field parameters against the physical properties. We can bring in all this curated data I mentioned to train the force fields. And so hopefully out will come a force field, which can be benchmarked, validated against experiment, and either that goes round again or it's released. And you'll have seen the Parsley and Sage releases in the literature, which are described in more detail down here. Just to say a bit more about that data, all of the bonded parameters are trained against a huge amount of curated quantum mechanical energies and forces, all of which is stored out in the open on QC archive. And all of the non-bonded parameters are trained against lots of mixture, enthalpies, and density measurements, all taken from the ThermoML, for example. And one more important ingredient, which was alluded to this morning, is how to go about assigning parameters to molecules. So open force field uses this Smirnov or Smirk's native open force field specification, which is an example of direct chemical perception. So this bypasses this atom typing that was mentioned earlier and assigns parameters to atoms or bonds or angles or torsions by directly processing the molecular graph. So shown on the right here is an example from this paper, assigning a bond to between a carbon atom here and a nitrogen atom here, but not just any nitrogen atom, it's a nitrogen atom that's also bonded to another carbon and another oxygen. So the details are not too important, but what this all means is that it sort of avoids the proliferation of force field parameters which come with the inherently come with the atom typing, and all this without a loss of accuracy. So shown in this table are the sort of number of lines of force field parameters that you need to describe all of these various force field terms in a few different force fields. And for Sage open force field, that's really just a few tens of lines of parameters. That means, importantly here, you can go away and start training new force fields quite automatically and robustly without having a big army of people to work on it. So that's roughly where our first collaboration with open force field comes in. We know that accurate determination of molecular conformation is really important, and this is largely determined by this rotation about flexible bonds. But with that quite small parameter library, describing all of these rotations in any chemical environment is quite tricky. So shown in blue here is a typical quantum mechanical scan for this sorts of molecule. And using a couple of common force fields, we can see that the shape's roughly right, but the relative energies of two conformers is not that great, and even the minimum is offset from the QM minimum. So we, led by Josh Horton in the audience, developed open force field bespoke fit as a means to supplement the parameters with bespoke molecule specific parameters. So the idea here is that a molecule comes in and all of the rotatable bonds are identified. The molecule is fragmented around each rotatable bond to include as much of the chemical environment as is necessary, but no more. Bespoke Smirk's patterns or Sparks patterns are assigned to the bond, and these are transferable back into the parent at the end. And then we do all of the usual reference quantum mechanical scans and parameter fitting. And all of this is compatible with the open force field infrastructure and QC archive, so we can really generate parameters at scale using data stored on QC archive. Did I show? Oh, yes. And of course, once you do the fitting, then all of the your potential energy surface matches the QM nicely. As well as that, by interfacing with QC Engine, we've got access to a huge number of reference methods for generating reference data. So in this table, we're looking at a measure of how well the geometry matches quantum mechanics. and how well the energy matches quantum mechanics. So we've got the baseline force field at the top, and we've got our full-on quantum mechanical fit at the bottom. And above that, we've got this hierarchy of different methods which we can use to speed up the fitting. So we've got semi-empirical methods, machine learning potentials, QM performed on semi-empirical structures and so forth. So recently, Josh has taken advantage of that. So Josh now works with Open Free Energy, and this is also in collaboration with ASAP Discovery. So he did a huge benchmark training of over 1,600 torsion parameters across more than 180 drug-like molecules, using the very nice AIMnet2 machine learning potential as the reference to train against. So as we expect, SAGE agrees reasonably well with AIMnet2, but after fitting, the energies agree much better. And he's also taken those bespoke fit force fields through to relative binding free energy calculations, calculated for 9 different targets, using standard open free energy protocols and a very nice alchemical scale execution system for planning the free energy calculations, submitting them, and bringing back the data. So the statistics for all of those targets are shown on the left here. So on the left-hand side, you've got the energy errors, so RMSEs of around 1 to 1.5 kcals per mole, and various correlation metrics. Now, I'm not going to pretend that one of those force fields is better than the other. I think they're pretty much performing equally well. So that might be surprising at first sight, but actually this seems to be matching a few other studies which are starting to come out directly using machine learning potentials in free energy calculations with mechanical embedding. So yes, torsional parameters are important, but there's other stuff going on in there like sampling and other parameters. So my philosophy is if the bespoke fitting is easy and fast enough, you may as well do it so that you have trust in your final force field. But talking about those other parameters of the force field, another study we've been looking at is looking now at the non-bonded interactions between molecules. So I mentioned that this is typically done using Leonard-Jones, not because it's any good, but because it was cheap to compute and has got kind of baked into all of the force fields. So we said that the open force field infrastructure is built to allow us to go in and make changes to this. So let's test that out and see if we can do it. We just need one more ingredient before we can do that, and that's the Smirnoff plugins package. So this is a flexible framework which extends the open force field style force fields with custom interaction potentials. So with the plugin, most of the terms in the force field are handled by the toolkit. But any terms it doesn't recognize, it goes to Smirnoff plugins and says, hey, I don't understand what a damped Buckingham 6.8 potential is. Can you tell me what its mathematical form is? And can you give me some parameters? And I think these are the parameters for water. So all of these force fields then are available to the entire open force field software stack, including force balance and evaluator, so we can go away and optimize these parameters as well. So as a proof of concept, we decided to have a look at this double exponential potential, which was in my talk title. So this wasn't come up by us, it was suggested by these folks here. And as the name suggests, it's made up of 2 decaying exponentials, one positive at short range to model the repulsion, and one attractive to model the longer range attraction. So the epsilon and the R min have the same meaning as in the Leonard-Jones force field, but it's got 2 extra parameters, alpha, which defines the steepness of the repulsion, and beta, which models the decay of the attraction. So it's quite flexible. So plotted here is the interaction potential between 2 oxygen atoms in water. So I've plotted tip 3p here in blue, and orange is a previously optimized double exponential potential, which closely follows the tip 3p model. There's tip 4p in green. In red is a more complex Buckingham 6.8 potential suggested by Christopher Rowley's group. And in purple is a model that we fit here using double exponential potential form, but starting from the Buckingham 6-8 curve. So it's flexible enough to handle any of these cases. So we took that water model and we trained it across a huge range of physical property data across a range of temperatures. So plotted here is our model. Which one is it? In orange, double exponential Buckingham 6-8 in orange, closely mapping the tipped ball P force balance and experimental data here. The previously published TIP3P model was only fit at a single temperature, and you can probably tell which one. And that really highlights the importance of fitting across a whole range of physical property data when you're developing these models. But we didn't want to stop at water. We wanted to go to a whole transferable force field for organic chemistry. So we've used that open force field fitting infrastructure to train that up. So we've done a complete refit of the global alpha and beta parameters and the epsilon and R min parameters for 15 different SMERCs or open force field types. So all of this was trained against more than 1,000 physical property datas, and the errors in the training set are tabulated here. So we've got pure densities, so double exponential here is doing a bit better than the open force field Leonard-Jones model. We've got binary densities of mixtures, again doing a bit better. And we've got enthalpies of mixing, and again, we're doing a bit better there, as we might expect, because the force field has a bit more flexibility than the Leonard-Jones. Just to wrap up a couple of small points. So we're using AM1 BCC charges throughout. We also trained all of the valence parameters to be compatible with the double exponential using the standard open force field protocols and tested on a load of torsion scans. And actually the Leonard-Jones and the double exponential force fields perform equally well on that test set. And I've put some timings here as well for like 1,000 water molecules in OpenMM. And it's a bit slower than the Leonard-Jones, but not significantly. And we haven't really optimized anything yet. So I promised some free energy calculations. So we can use this potential in free energy calculations. So what we need is, if we take the full interaction potential shown in blue, we need to be able to scale that interaction down with some lambda parameter. So ideally, we've just wanted to stick a lambda parameter in front and scale the lambda between 0 and 1. Unfortunately, that didn't work very well. We didn't get this nice smooth interpolation between 0 and the full interaction. So we had to also scale the alpha and beta parameters. So we scaled these down close to 0 and close to equal to each other. And it turns out that gives you this nice form like this. And also good overlap between neighboring lambda windows. Shorter time, so I'll speed up a bit. So we applied this to some transfer-free energies. You all know the definition of a transfer-free energy, I think. And these correlate pretty well with experiment, with an error of about 0.85 kcals per mole, similar in accuracy, a bit better than Sage Leonard-Jones. So I'll wrap up there. So we've used open force field infrastructures. We've contributed in bespoke fitting parameters to train dihedral parameters, and this Smirnov plugin tool for substituting in new functional forms. I wanted to emphasize that this would have been prohibitive a few years ago, but steps forward like this in the direct chemical perception, high quality data, the robust infrastructure, all make this possible in a few weeks. So we can really look at systematically exploring these force field choices now. It was a bit too early to talk about them today, but some things that are coming are improvements to the bespoke fitting workflow, investigations into new valence functional forms, we can do that too, new charge models with higher level QM, and we're also interested in machine learning potentials. We released the MESOF model in collaboration with Gabor China's group a year or two ago, and we're looking at embedding those within MM force fields. So with that in mind, do talk to Josh, who did all of the work here. He's got a poster on that bespoke fitting workflow. João Morado from Julian Michel's group will be talking about some of our electrostatic embedding work in the first poster session. And Finley Clark has now joined my group and the Open Force Field Initiative, and he's working on those things that I mentioned, but also talking tomorrow on free energy calculations. So with that, I will thank Newcastle Group, everyone at Open Force Field Initiative, everyone on the Bespoke Fit benching workflows led by Josh Horton, and also Josh, Simon, Pavan, and David, who worked on the double exponential potential, again led by Josh. And thank you for your attention. I've not thought about it personally, to be honest. Yeah, I'd have to sit down with a piece of paper and see what we can do. To be honest, I'm not 100% wed to the double exponential. I'm not saying we all have to use that next. It was really just a proof of concept to put the infrastructure in place. If anyone here has an alternative functional form, which maybe has that nice natural soft core potential with any other mathematical properties, happy to have a look at them. Yeah, it does make a lot of sense. Yeah, so we only fit the double exponential parameters initially against the physical property data. So that's using the AM1 BCC charges. So yeah, I also agree that there's a few things kind of baked in which favor the Leonard-Jones a little bit, maybe like the combination rules. Also the fact that we're starting close to the Leonard-Jones potentials and then optimizing from there. So you can imagine that would include a bit of bias as well. So I definitely want to look at methods for removing that bias from the fits. Don't quite follow the question. What do you mean? Yeah, so we're always performing these full torsional scans when we're training up the torsional parameters. So there's no real bias to any conformer. Oh yeah. Josh will shout if I'm wrong, but I think that's the total error over the entire potential energy surface. So again, no conformer bias. Yeah, it's a good question. Yeah, like I said, as I was going along, the double exponential just has more parameters in it. I think Michael Schertz and team have done some nice work about sort of penalizing complexity in functional forms. So we might need to look at something like that.